I think it's great. I think it's definitely like a good idea if you're like looking to get involved in the C++ industry to come talk to the people, to meet everybody. You never know what can happen.
All right. Hello, everyone. Welcome to my Back to Basics talk about object-oriented programming. I'm Andreas Fertig. I am the one who created a tool called C++ Insights. We will see that during this talk a few times to peek behind the scenes. I've also written a couple of books about C++. I think they are out of them here at the CPP cache, but you can still fetch them online or on Amazon. My day job is providing training services, so I'm available for in-house classes on-site or remote, whatever you prefer. I also work together with the CppCon Academy here, which hosts pre- and post-conference workshops. It's a very short notice, but you can technically still book my post-conference workshop happening tomorrow and on Sunday about modern efficient C++. You still have a chance to book Nikolai Yosit's class. It happens, I think, only on Monday, so it gives you more time, and it's online, so more feasible. If you prefer to learn more at your own pace, I have a self-study course. It's practically a recording of my classes. It's about C++ 20, so you might want to check that one also as well. I'm German. I now met a lot of people during this conference and in other conferences who either speak German, are German, or at least understand a little German, so you might be able to tell from my last name. If you're not, you can translate it to English as finished, ready, complete, or completed. So I think it's a very nice positive name, right? It's an adjective in German that occurs frequently in the language, and when I was younger, I made jokes with my friends how rich I would be, or the rest of my family, if we would get a cent every time when somebody uses our last name, right? So trademarked. It's not happening, luckily. But whenever I give these talks now, I'm looking a bit more into my last name. And I recently discovered the following. We had the Summer Olympics in Paris, which wasn't what I discovered. I already knew that. But it was, I would say, the first time that I realized that the sequence they shout when they start a race or swimming is ready, steady, go. And I just taught you the translation of my last name. You can translate it to ready. So whenever they start a race, not only at the Olympics, they start a sequence with my last name. Quite interesting. So before we dive into C++, let's continue with this other language lesson. I just taught you how to translate my name to English, right? How about translating that sequence to German? Are you ready? Steady. Go. This is how it looks in German. You would have failed translating that, right? So ironically, we start a 3-sequence part with 3 words. So you have to listen and very careful in German, otherwise you would start the race too early. And then my last name goes second. It makes sense if you look deeper into the language, but it only shows me that languages are an interesting thing and can be complicated. It doesn't matter whether it's the spoken ones or the ones we just use on our computers, right? So let's dive into what you're here for potentially. Not the best German trainer, I guess. I suck. I'm better at C++ grammar-wise than at my own language. So it's about object-oriented programming. So let's start with the basics, a class. I assume you're already familiar with that, you saw that. So we start object-oriented programming in C++, usually with a class, because it's about encapsulation. We want to model objects. So we start this by using the keyword class, giving the class a name, in my case here, Apple. And next we have the decision to make in which access region do we want to put things. We have practically 3 different choices there. We can say something is in the public scope, that means visible and reachable by everybody. You can also put it in the private scope to say it's only reachable and visible to this class, which is the main thing about object-oriented programming. We want to live in a world where we have this encapsulation and when we can have private data to the class and can control the access to these individual members, which is a different thing, for example, compared to C structs where everything is accessible. We have technically a third kind of specifier that's protected that comes into play when we derive from a base class. Then protected means that whatever in that scope is not reachable by anybody else other than the class declared it and all its derived classes. So this is how you can give your relatives more access to your private data than anybody else. Assuming you don't share everything on Facebook you do, that might be something you want to go for. Now, since class is about having private data in it, we can also see at the bottom of this class in G here, we have a private data member, right? You should always have a good reason to declare data members public, because one thing about a class is having the things private and having access functions to them. Since that, we require a constructor, which you see at the top in B here. Since this is a one-argument constructor, I marked it explicit because one-argument constructors are also referred to as converting constructors, and the compiler is allowed to use them whenever it's looking for a conversion sequence. And to not make that happen, well, unwanted or unintentionally, we tend to say best practice is to make our single argument constructors explicit unless we really want this conversion to happen. Now, once we reach that point, it's about initializing the data members. And I show you that in C here. I start a sequence with a colon. This is the so-called constructor initializer list. Please, please, please initialize your data members there. Always. This is the place to do that. This is the place where it will always happen. If you have an object in your class that's default constructible and you move your initialization into the constructor's body, it will still be initialized in the constructor's initializer list. You cannot prevent that. You will fail if your type in the class is not default constructible, then you will get a compiler error message because the compiler always tries to initialize the objects there. So this is where you should put them. Otherwise, you simply risk that the initialization happens 2 times. So this means in D here we have the constructor's body, and the constructor's body's purpose is to be there to ensure invariance. We will see an example about this in a few slides. Then I have the 2 member functions here, set and get. The one, as the name says, is to set the data member, the only one I have in this class. The other one is to fetch its value. The one difference between the 2 you can see is set here is just written out like a normal function, while get comes with a const at the end of the function declaration. And that signals to your fellow developers, to yourselves, and to the compiler that when we call this function, the state of this object does not change. This is the promise you're getting. Okay, so this is something valuable. You might hear something like terms like const correctness, where we can build chains on const objects. So whenever you have a getter that does not modify the state of your class, be kind, make it const. It's the correct thing to do. Down there in main then you can see I'm using this apple object. I use Alice here as one sort of apples, and I call set and get respectively on this Alice object. Now let's use C++ Insights for the first time here to peek a little behind the scenes. For those who haven't seen C++ Insights, this is how it looks. You can also use a command line version. Its main purpose is you put in C++ source code on the left, you get C++ source code out on the right. It's brilliant, right? $1 million idea. Nobody paid for that so far. The real thing that C++ Insights does is it annotates what it spits out on the right with the things your compiler does to you. In this specific case, C++ Insights looks on everything with the eyes of Clang. Okay? You have a default mode where you can translate that. I have also a special mode enabled which says show C++ to C transformation. I apologize that in front of a C++ crowd I will show you more C code, but the purpose here is to help you understand how classes internally really work. And you can see a couple of comments here for the this pointer. So whenever we access either member functions or data members of a class, it's up to us whether we want to prefix them with the this pointer. So I did that in the constructors initializer list at the top. I put it in a comment. I put also a comment in set here, and I didn't write anything in get. My personal experience is years ago when I started with C++, I always spelled out a this pointer because it helped me create a reference to this thing belongs to a class, whether it's a function or a data member. Nowadays, having become a little more gray than back in the days, losing hair and so forth, so it's a long time back, I consider it a noise. It's a distraction for me because I understood the language well better now than back then. So I personally prefer not writing the this pointer anymore. But I just want to say it's up to you, whatever it helps to make your code more readable, more understandable to you, do it. And maybe you will change later in the course of the day. So if I now hit the transform button for the first time, then we can see how this classing in C++ looks to the compiler. So because the language comes practically from C, there is no such thing as a class, you can say. To the compiler, it's just a struct, my class. It comes without any member functions. It's just aggregating the data. We also can get rid of the public, private, and protected. This is just a firewall between us users and the compiler. Once we are inside the compiler can do whatever it wants. It doesn't technically need everything of that anymore. Our constructor, it's just a function with a funny name. There come a few special rules into play. You're not supposed to take an address of that special function and so forth. But that's it. The one interesting point that the constructor has in common with all the other member functions is the so-called implicit first argument, the this pointer. So to every member function you call in C++, the compiler injects this pointer. In C++ 23, we, I think, gave it a better name. It's now called the implicit object parameter, because that one donates to the object. So what we have here, it's a free member, it's a free function, right? And via this pointer, we tell this function, hey, this is the object you're working with. This is the data. And this is where you have the choice to either say this the entire time yourself or let a compiler fill in the blanks, which it is really good to do usually. I'm using the double underscores here for this to make it work with regular C++ code, but this just for the purpose of generating the code here. You can see this now is the same for set. We have an implicit this pointer as the first argument. This is the same for get, which only has this implicit this pointer. The difference between set and get is the constness of this pointer. So when you declare a member function as const, this translates to the this pointer becoming const. So it's pointing to constant data. And this disables us from changing any data there. So this is the trick we are practically doing in the background. If we now go further down the lines, let's just have a look at that. We can see what the compiler now does is this piece here. It creates this apple object on the stack, which in this translation is just a struct. It calls this function with the name constructor in it, and it passes a pointer to this Alice object as the first argument. So this is our implicit this pointer, the object parameter. And then it has any other arguments that might follow or not. In my case here, 3. The function set, or more specifically on the left-hand side, the member function set is now just a free function, also getting the this pointer passed in as the first argument. So my Alice object pointer here. And the same thing happens for get. So this is the behind-the-scenes view, what happens if you're using a class. So I do training, right? And I taught many classes in the past now, teaching C developers how to write C++ code because companies do the transition. And either with them or with university students I also had, or sometimes even with a more experienced crowd, one question that comes up is, Andreas, what's the difference between struct and class? We are using class if you're creating an object like here, but I saw people also doing struct there. And one of these people could be mine, because for slide code, it saves me one line. Only having 24 lines, it's real safe. So what's the difference between struct and class? The default visibility level, the default access level. That's the only difference. So see it like a struct coming from C. C doesn't know any access specifiers. Everything is shared. Everything is public. And in C++, we took that model over because we are compatible to C. So if you declare a struct, like I did it here with an int member and some function, the function would be invalid, by the way, in C, but you can have it in C++. That means that m value here, as well as fun, are publicly accessible. If I write the same code and change struct to class, m value and m fun on the right-hand side are now private. Nobody would be able to reach it, so that class would have no purpose because nobody can call fun. And you cannot initialize the data member, practically. This is really the only difference. You can have virtual member functions in a struct. You can use access specifiers. You can say that you, after the opening curly brace on the left-hand side, you write private or protected, whatever. You have the full flexibility. So it's really the default visibility that's the difference between the two. Okay. And as I mentioned below, you might see me often using struct instead of class because in this slide code, it saves me one line. And with 24 lines, that's something. But in real code, I tend to use class whenever I write an object. Which brings me to my next point. Now that I pointed out that there's basically only the difference between the access level, when to use struct and then to use class if you're not producing slideware here. And one rule of thumb I have is I personally use struct whenever I only want to aggregate data. And this data has no relationship to each other. My example here being the struct point. Point comes with two integers, x and epsilon. Any value and any combination of values of the twos is a valid combination. There is no dependency. At least not as modeled here. So I make that one a struct because I don't want to write a constructor that simply forwards setting these members. You can read them out, I'm happy. You can set x without setting epsilon. Well, it's okay if you move along the x-axis, fine. I use a class whenever I have an invariant to check. And my favorite example is date. Let's assume we have strong types for year, month, and day. I'm not sure what range we would give a year. So let's say we have some reasonable range there. We can nail it down much better for month and day. We all know month range is from 1 to 12 or from 0 to 11, however you want to count. Day range is from 1 to 31 or from 0 to 30. Okay, so we can limit this type. We can say we have a strong type here. And we know that each of the values is in a valid range. Now, if we create a date, like I have it here, and we call the constructor with year, month, and date, all of the three values are valid themselves, but whether the combination results in a valid date, that's a different question. The 31st of February is always an invalid date. The 29th of February, well, every 4 years it is, but specific 4 years, so not just 4 years. So whenever I have a situation where the parameters, the members I try to set, depend on each other, I defer to a class. I tend to set simply the members in the constructor's initializer list, and in the constructor body, I now check the invariant. Is this date combination valid? And if not, depending on what code I'm writing, I'm throwing exception, invalid date. I might set the date to a well-known, unknown, or invalid date, or set it to the 1st January of 1970, like Linux does, things like that. But this is what I'm doing then in the constructor's body. So this is still the difference. I'm setting the data fields in the constructor initializer list and to do the checks in the constructor's body. This is what the constructor's body really is there for. And this is where I draw the line between a struct and a class. Whenever there is something I want to guard, whenever there are things that have a relationship to each other, I use a class. And otherwise, apply a struct. Okay? Now this title might sound funny because I assume you also already might have written a class, but the question here is how to declare a class, and more importantly, why. So this here is the default pattern that I was taught when I started programming and that I had for a long time. You can also see that in C++ Insights, which now is, I think, 5 years or 7 years old, something like that. We start by saying class, it's a string here. We start by saying, okay, now we start the public scope. We have a default constructor in it. We have the copy operations. We have the move operations. Oh yeah, we have a destructor there and then potentially other member functions following. And at the very end of the class, in the private section, we declare all the data members. Just by a show of hands, who does it in a style like this? All right. Interesting. So not that many, thank you. I do a lot of teaching. I also do code reviews. And something that I realized doing that is the data members are very important. So having in a class to figure out where the end of this class is, that costs time, especially in your real world code. And the real world code I'm working with, it's not just 70 lines of code in a vacuum. So it's way bigger. So finding, oh no, that I went too far, that's already the next class. So the pattern I now do is saying, I move the data members up. So the first thing, that only means I do not have to change the access level because they are private by default. And then the next thing is, and this is my personal preference, I tend to declare the default constructor. I want to know whether this thing is default constructible. And the next thing that's very important is, does this class has a destructor? Because that means that some special handling is going on there. If it doesn't have one, well, we rely on the defaults, that's fine. But if it has one, it might be needed a special treat. And then I tend to declare the copy operations, and after that the move operations. I usually have them together, so copy constructor, copy assignment operator. And after that, the other functions that make this class really valuable and valid, they come into play. I linked you an article below that's from Howard Hinand. He also inspired a little bit my change in the class design. He has a little different style. I think he puts the destructor first for a different reason. So I can only encourage you, if you wanted to improve your style writing classes, also give Howard Hinand's article a shot. It's really worth a read. And if you're still doing the thing on the left, or if you never give it a thought, how to declare a class, maybe other things are important for you, I can only encourage you to think about that. It's not written in stone. You can change it, and whatever you benefit from, whatever enhances your productivity in code reviews or other things, do it. It's not just about documentation. Sometimes you want to look at the internals. Okay, you can have a very, very well-written documentation, but still you want sometimes to peek into the things. And since we are all developers, we do that a lot of times. So give that one a shot. If you're talking about creating types, we can basically create two different types. That's value types or reference types, also sometimes referred to as view-like types. If you have a choice, go for value types. Value types means creating your type and follow the rules as int do. So do everything as ints do. That's the main idea here. Scott Myers coined the term a long time ago. The idea here is, if you look at a standard library, std vector, std string, they do everything for us. They allocate the memory, they allocate more memory if required, they destroy the memory. they duplicate the memory in case of copies and so forth. So it's not about us saying, hey, string, we have some piece of memory here, please use that. Oh, it's too less for you, all threads. The string handles everything. Like an int, we can default construct it, we can assign values to it. So this is the spirit of creating value types here. The other thing would be creating reference or view types. We have a few of them now in the language in form of span, string view, and other things. This means that these types do not own data. They refer to it. That makes it more difficult to handle these types because you have to keep lifetime in mind. The reference, the view type, has to have a shorter lifetime than the thing it references. If the reference thing goes out of scope first, you look at a dangling reference. And this makes handling these types more difficult. They are valid, they are useful, but they might be more difficult to handle. So keep that when you're doing class design in mind what to do here. Now here's a brief overview about the special member functions and the class operators that you encounter in a class. Say I have a class called CPP. In A here you find the default constructor. It's the one coming without any argument. Technically not a special member function here is the constructor I show you in B. It's the one argument constructor, also called the converting constructor. In C then, the class name with the tilde in front, it's the destructor. In D, we have the copy constructor. It takes a type of the class by reference, typically by const reference, but if you are working in an older code base, you also might see that without the const, so that's still valid C++. E then is the copy assignment operator, so it takes a const CPP object by reference and returns typically also a CPP object by reference. And then we have in F and G the move constructor and move assignment operator, something I'm not going to talk about today. If you look about how this translates to code, then you can see that if in line number 3 on the right, I create a object of type CPP on the stack and use empty curly braces, I invoke the default constructor. If you look down to line number 4, I create my object B of type CPP and I pass in the number 3. That's not of the class type, but supposedly it's a type that my CPP class accepts in a single argument constructor. This is why it's called a converting constructor. I'm converting an integer to a CPP object here. So this is where this constructor B is invoked. I'm not showing you the destructor here because we usually do not invoke it directly. It's either invoked when we are leaving the scope for stack objects or when we are calling delete in the background. Then in line number 6, I invoke the copy constructor because I create a new D object and passing the A object that already exists of type CPP to it. And subsequently in E, I assign an existing A object to an already existing B object. This invokes the copy assignment operator. So we are doing a copy here. Okay. So this is how the special member functions and the class operators work together. Now this here is a table that you either hopefully are familiar with or now learning about. It's also put together by Howard Hinnant. It shows what the compiler declares depending on what we do to our class. And I guess you're all familiar with the first line. If you do nothing to your class and struct subsequently, you get a default constructor, you get a destructor, you get a copy and the move operations. Everything is just there. This is C++. This is the spirit. Now, the next line is something that bit me real hard, at least in the beginning. If you provide any constructor to our class, that would be a single argument constructor, the default constructor is no longer declared. So our class is no longer default constructible. I don't know how many times that bit me in the beginning, and I didn't simply understand why that thing doesn't compile anymore, because I missed the default constructor. Copy operations, move operations, they remain there. If we provide our own default constructor in terms of the standard, that one counts as user declared, the rest remains the same. Now the line where we declare our own destructor for a class, that one is interesting. We still get the default constructor. Our own destructor now counts as user declared. In this slide here, you can see we still get the copy operations, but if you look further, we just lost the move operations. And this is a learning inside the standardization community based on feedback and real-world experience, I would say. Back in '98, the spirit was like at the first line that the compiler should provide all the special member functions for us developers as long as possible. So the spirit there was, well, if you have a destructor in your class, sure, the compiler can create the copy operations for you. Are you sure? What about that case where I happen to have a pointer in my class, I allocate memory in the constructor, and I destroy it in the destructor? Remind me, what does the compiler generate for the copy operations there? Oh yeah, right, it only duplicates the pointer. So you're running into a double freeze situation or worse if you're copying this object because you're not copying the memory behind it, or more precisely, the compiler doesn't do for you. So this is obviously a pitfall you can run into. And if you think from a different perspective at this, so more like talking to your compiler, hey compiler, you don't know how to declare a default destructor. I do that for you, but feel free to still create the rest. We just tell the compiler that it is not able to create the most valid thing of our class, the destructor, but we assume that it's still able to create the rest. And this was a change of mind. So this is why in C++11, when we added move operations, we said, all right, if a user provides a destructor, compiler no longer generates the move operations. The behavior, by the way, that you still get the copy operations is deprecated since C++11. So you're looking at a future where you will also lose the compiler generated copy operations in case you're supplying your own destructor. Okay, keep that in mind. The rest now, the copy operations always depend consequently on the move operations and vice versa. This is why when we declare the ones, we lose the others. So you have to be more careful about that now, but it makes our code better in the end. Now let's get started with talking a little bit about polymorphic classes. So we basically have three keywords that deal with polymorphism in C++. We kick everything off with the keyword virtual. That means we mark a function as a replaceable function by a derived class. Replaceable means the implementation. We can change it in a derived class. If you do that in a derived class and you're using C++11 or newer, please use the override keyword to declare your intention in the derived class to override a function from a base class. You get more checks from the compiler, like does there really exist a function with that name and that signature in any of the base classes? And if not, you get a compile error. But we are backwards compatible, so using override is somewhat optional. The other option you have is to say you declare either a class or just a previously declared virtual member function as final, and by that ending the inheritance hierarchy. So if you declare a class final, it means after that point nobody can derive from that class any further. If you declare a member function as final, nobody can override that one anymore later on. I've seen the keyword final used a lot in generated code by different code generators because the class layout and everything might change every time it's not meant to be a base class. So we mark that one final. So these are the three main things. And if you now start looking at virtual member functions, then I can create a hierarchy like that. I have a base class fruit. Fruit here has a double M weight in it. It has a virtual destructor and a virtual member function called print, which simply prints out that's the base class. And then I have a derived class. I'm creating a apple object here, which derives from fruit. Apple brings a ripe grade to the table, saying how ripe that thing already is. And it also has a print function. But I'm using the override keyword here to override implementation from the base class. And now I go into a specific sort of apples, the pink lady. So that means my pink lady here derives from apple. And pink lady comes with a color shade, how pink or ever it is. And it also overrides the print member function. That means it overrides the one from apple that it inherited and the one from fruit because they are the same. So whenever I now have, like down there, a pink lady object I call delicious and I invoke print on it, it means the print member function from Pink Lady gets called. And the beauty and why we are doing this about virtual member functions is that we can use a base class pointer now and call print on that, and the correct, hopefully, member function will get called. So what I'm doing here down there in B is I'm static casting my Pink Lady object to the base class fruit, so to a pointer of base class fruit, and then I'm evoking print on this F fruit pointer. And this will still print out the Pink Lady printout because the compiler understands the inheritance hierarchy here. And this is what we are often want to do because we are treating the base class like an interface. And we are just passing around this interface, and everybody can then adjust the implementation and it will be invoked. Now, if you peek behind the scenes here a little, and I would say bear with me there. If I once again use the C++ to C transformation and I translate that thing, you can see a lot of things we really don't have time to go into in depth. What a compiler basically does, and this is based on CFront, so the first C++ compiler back in the 80s, they're doing this slightly different and better nowadays, but it gives you an idea. They have a pointer declared, type def2 pointer, we call that a virtual function pointer, and then they have a struct here, which the most important thing is this vpt, so this is our pointer to some function. The signature you see here doesn't really matter because we cast it to the correct one later. We have a forward declared array called the vtable array that exists in your code. You can sometimes also see that, especially on the Linux. And now we are seeing what we already saw, right? A class is just a struct. But since I now have a virtual member function in place, the first member that the compiler injects here is the so-called vtable pointer. This is of this type mptr here, and I call it ptr fruit to say it's from the fruit class. Followed by that are all the data members that I declared in this class anyway. Now let's skip over the destructor, over the print function. In the constructor of fruit, we see the pattern that we already discussed, right? We got an implicit this pointer here passed, and the first thing the compiler now does is to initialize this so-called vtable with what we will see later, the first element of this vtable array. And then it initializes the rest of the data members in your class, and then it returns everything. And this now is building up. If we look at the YAPL object, which derived from fruit, it also has a vtable pointer, and it's a combination of the data members of apple and fruit. So it has from the base class the mweight data member, and from its own declaration the mripe grade. In its constructor here, it calls the constructor of the base class to make sure it initializes all the data members that come from the base class, and that it initializes the vtable pointer. And by that, it overrides anything that a base class might have assigned to. So now what the derived class does counts. And then it initializes all the rest of its own data members, and the pattern simply continues for the next derived class for Pink Lady. So every class here has only one vtable pointer. That's the key takeaway. And if you now look down here, and we can see what the compiler creates for us is this vtable for fruit. It consists of two elements, and let's ignore the numbers for now. You need that if you have multiple inheritance. It assigns the destructor to the first element, or pointer to the destructor, and pointer to the other member function that I declared virtual as the second. So this is index-based. Basically, the compiler understands and knows which member function is in which index position in your table and indexes it by that. Then below, I have this vtable array that we saw the forward declaration before. There, the compiler simply inserts fruit, apple, and Pink Lady in their respective order. It remembers the order. And if you now place a call to such a virtual member function, I know it looks ugly. The line here is this one. So what the compiler here practically does is it reaches for the vtable of this object, fetches the member function that we're about to call at a specific index, and casts that thing to the right function, to the right signature, and then invokes it. So the most code you see on the slide is just instructions to the compiler how to cast it, to make everything type safe. And the thing that you really have in your code at the end is the access to the vtable, figuring out the correct position there and invoking the function. So this is how virtual member functions in the background work. Okay, that's at least a brief intro to that. Now, let's go to something else, default parameters. Has nothing to do with classes, I understand that. I assume you know that you have a function, a free function fun. It takes a single argument x, and I can default that to 23. Whenever I now invoke fun, it simply works, and the value of x is 23. And to be honest with you, I never really cared about how it works. I stumbled over that as a side effect when I developed C++ Insights. So this here is C++ Insights showing you what the compiler does, and it's incredibly simple. It takes that default value that we provided out of that function declaration and inserts it in all the places where we left it out. That's the basic trick. Okay? So the original function, remember we want at the time stay compatible with C, doesn't know anything about default parameters. Just drag it out and insert it wherever we need it. Now, keeping that in mind, what if I change the code a little? Let's say I have function fun that takes a std string x, and I default that one to a string like hello C++ community. I'm a default parameter, and by the way, I'm really long, so I'm exceeding the regular 16 characters that fit into a small string optimization. It's important here. And because it's so fun, I'm calling fun 3 times below in use. If you look at the same code with the knowledge that you just gained or already had, maybe, then I think it's clear that fun here creates, in this specific example, 3 std string objects. And that means it does 3 allocations and 3 deallocations. So as good as I would say default parameters might be in some scenarios, when it comes to built-in types, they can be really expensive if we are talking about class types. So keep that in mind. And I have this entire example in here because of a specific other reason. We wanted to talk about object-oriented programming. That means classes, right? What if I have a scenario like this? I have a base class car, comes with a virtual destructor, comes with a virtual member function drive. Drive here, I use a default parameter to say, well, it's a bright idea to let a car drive backwards by default. That doesn't hurt anybody that's in front. Brilliant. Now I have 2 specific cars here, a Tesla and a Toyota, both derived from car. Tesla is happy with everything as it is. Toyota says, well, it's smarter to let the car drive forward by default because somebody might stay behind the car and get hit. Okay? They both override the virtual member function from the base class. And now in use, I create 2 unique pointers with the help of make unique, one of type Tesla, one of type Toyota. The difference between the 2 is, for Tesla, I store it in a unique pointer of car, so in a base class pointer. For Toyota, I store it in a Toyota pointer. And then I let the 2 drive here, I let the Tesla and the Toyota drive left, and I'll let the Tesla drive without any arguments, letting the default arguments kick in. Which direction does the Tesla take? In the last line. You can also say which direction you want it to take. It's fine. Are you ready? Here's the answer. 3, by the way, my friends, is backwards. So Tesla, without any parameter here, drives backwards. Despite the fact that in the derived implementation, oh no, I messed that one up, right? Sorry. It's an oversight on my part. I wanted to say this one here. Let the Toyota drive as a base class pointer. And then we can see, and this is the point I want to try to make, that my Toyota here drives backwards despite I said drive forward please in the default implementation. And the reason for that is that we have static binding. So the compiler looks at compile time at the type of object. And in my case, for Toyota here, I have a car pointer. So the compiler goes to the car class and looks up what's your default parameter if there's any, and it inserts that one. It doesn't know about the polymorphism that comes in later. So this is why you should stay away from default parameters when it comes to virtual member functions, because usually you only create hurdles for yourself and your colleagues. It's a good idea to not do that. Let's talk a little about treating the destructor. You've seen me doing that for some time now. Let's suppose I have this class IO port. IO port comes with a default constructor, with a destructor, and a virtual member function flush. Then I have a specific port version, a USB-C port here, comes also with a default constructor, a destructor, and it overrides flush from the base class. Now, in main, in A, I'm creating a unique pointer of IO port. I use make unique to create a USB-C port. In fact, I can call port flush on that thing. So everything looks good, right? If we use Compiler Explorer here to explore what's going on, I have puts here to show you which member function is invoked. We can see, oh yeah, IO port constructor called, perfect. USB-C constructor called, excellent. USB-C flush is invoked as intended, excellent. IO port destructor is called, nice. Oh, wait, where's the USB-C destructor at this point? The USB-C destructor isn't called. Because I made one slide change to the rest of the slides that I previously showed you, my destructor here is not virtual. And that means the same thing as we just saw, the compiler sees the type of IO port. And since it sees it has no virtual destructor, it only invokes the destructor of the class type it can see, and potentially class types beneath it, but not the one that I derived later from in USB-C. So you're risking not destroying your entire class. Now, it's not that easy to come up with a decision and treat your dispointer here, your destructor here. One scenario would be saying, okay, we declare the destructor virtual. Subsequently, we use override to override the destructor in the derived class. You can do that. If you do that, the meaning is that you're just opted in for a base class being destroyable, or sorry, for a derived class being destroyable via a base class pointer. Because now I can have a IO port class here, class type, and if I call delete on that, the derived classes, USB-C in this case, destructor will be invoked as well. So this is the code that I had on the slides the entire time, right? If you look at this now in Compiler Explorer, we can see the last two lines. First, the USB-C destructor is called, after that, the IO port destructor, pardon me. So this is why you want to have a virtual destructor. If you say you want to opt in to a derived class being destroyable via a base class pointer, this is just one design decision. I show you another one. Another one could be that. I say I have IO port, comes with a destructor, comes with a virtual member function flush, but I put the destructor in the protected scope. This prevents me effectively, or anybody else, from declaring an IO port stack, an IO port object on the stack. You can allocate it with new, but you also cannot delete that object because the destructor is only reachable by derived classes. So here I say I derive with USB-C from my IO port, I implement everything as before. I now can have these two functions, process and receive. They take either a pointer or a reference to that thing. I create a unique pointer of USB-C now with make USB-C, and I can pass the things to process and to receive respectively. But this is what we often want to do. We just want to have this common shared interface that IO port declares, but neither process nor receive should be able to delete any of these objects via the IO port pointer. So this is the difference. If you do not want to opt in for deletion via base class pointer, don't say so. Go to this pattern. The third option you can choose from is if you look at the string class that I earlier presented to you, and looking at studstring, for example, that class requires a destructor because we are allocating dynamic memory. At the same time, it would not be a helpful class if we make their destructor protected. We cannot create an object of that, we cannot delete it, so that's not an option. We can also maybe agree that string itself already brings everything to the table that we need. So there is no need for inheritance here. This is when you can use the keyword final to say, all right, I make this class string here final because it contains everything we need. With that, we can have a public accessible destructor, but we do not risk that somebody deletes only half of the inheritance hierarchy. So this is your design decisions, and there is no right or wrong. It depends on what you're really doing, implementing at this point. We can summarize that in this table here. We can say, okay, if we have a destructor that's public and the class itself is final, like in string, we just saw it. The meaning here is this class is not intended to be a base class at all, period. If we have a destructor that's public and virtual, that means this base class here supports deletion via a base class pointer. The first IO port version was such an example. It's a very common pattern. If we have a destructor that's only protected, that means it's not intended to be destroyed via a base class pointer, period. So these are the design options summarized in one table. Now, since we are talking about that, there is some other pattern I wanted to make you aware of. It's called the template method. Suppose I have this base class sort here. I opted in for deletion via the base class pointer, but it's a side note. It has the function process, which calls read, sort, and write, which are the three virtual member functions, the pure virtual member functions of sort, all in public scope. Now I have a concrete implementation of a sort algorithm, quicksort, and I decided to make that one final here. It derives from sort publicly, and it implements or overrides read, sort, and write. If you look at this code for a moment, why is process there? The reason that we have process is to make it easy to use for our users when they want to sort something, because there is the importance of the order. It doesn't make sense to call sort first without having read any data. You do not need to write anything if you haven't read anything. So there's an obvious dependency. And somehow you might look at this class and miss that and simply call sort. So this is the reason why we have process in there. The problem now is users see via the IDEs or with their own eyes, there is read, sort, and write, and they might be tempted to invoke them, right? But we do not really want to expose the three members here, the member functions. They are just there to make our implementation work. So what a template method now says and does is we still have this function process. It still calls the member functions in the correct order, but we move the virtual member functions read, sort, and write to the protected scope. By that, making them unreachable by anybody else than a derived class. And now my derived class overrides that, and with that we have a very clear interface to our users, and this is called process. It will do the rest for you. And the derived class decides the sort algorithm where to read the data and where to write it to. So keep that in mind. It's not always that our virtual member functions must be public. Sometimes it's just to provide a proper implementation, and some other function is really called to work with the data. Now here's one thing that's not so often talked about, and I call that one good class design. And we saw a good portion of that already. I'm circling back to my IO ports example. I have this destructor in here. I have a virtual member function flush, as we saw it. The destructor is in the protected scope. So I did everything, I would say, good in the terms of what I teach you so far. USB-C, as always, derives from my IO port, comes with a default constructor, a destructor, the member function flush, which is overrides from the base class. Now look carefully what I do in use. I created device object on the stack of type USB-C. I have this object copy where I assign the existing device to, so I essentially created a copy of USB-C. And that's totally fine. It's fully valid. That's what we want to be able to do. Now something, and please don't do that at home. It's obviously not that good code, but I wanted to use it to illustrate my point here. If you go down to line 21, I am allocating with the help of new AIO port object. Remember, I cannot place that on the stack because the destructor is protected, and I cannot technically delete this object because if I would call delete, the compiler would tell me the destructor is not reachable. So this is very limited scope, but I saw it sometimes happen in some embedded projects where I basically only allocate memory and never delete it. Compilers are the one real exception. I'm not sure if you're aware of that, but compilers usually only allocate memory. They never free it because they know at the end of their task, the program goes away anyway and your operating system will free all the memory. And freeing it between doing the job simply wastes time. So I allocate this IO port object here on the heap. And this now enables me to say, all right, I have this HM pointer here. I call it because it's questionable what I'm doing. But I can dereference that pointer and assign a device object to it. Because of the inheritance hierarchy, I can assign a derived class to a base class. I couldn't make the example bigger, it would not have fit on the slide, but use your imagination. Think about that my IO port class has a data member. My USB-C class comes with 2 data members. So if I'm assigning a derived class to a base class, when the derived class has more data to store than the base class, the additional data members from the derived class, they simply get cut off. We call that slicing, object slicing. So the code in a basic sense still works. You can do this operation, but we just lost important information. So I call that good class design because if you are opting in for good class design, you should consider slicing as well. And that would mean treating the copy operations and the move operations alongside a potential destructor. So here I'm going back to opting in for deletion via the base class, but I'm saying, okay, the copy and the move operations, they're protected. So only the base class can do that. And that basically disables the faulty behavior that I could achieve before. So these are all important things when it comes to object-oriented programming that you should consider. Here's a summary of all that. I would say prefer value types over reference types. They're easier to use and more regular to use. Declare the important things first in your class. I cannot really tell you what it is. For me, it's usually the data members and the destructor as well. Don't use virtual member functions with default parameters. I hope I made my point there, illustrated why it could be a bad idea. And if you're designing classes, design them either to be usable as a base class or not. Okay, that's a very important decision. Remember, a virtual destructor disables the move operations, so this is something you should consider, and it will supposedly remove the copy operations in the future as well. There were also the first compilers asking to enforce this behavior, and they are warning since C++17 or since 2017, I think, about that. Remember the last part we talked about address object slicing. This is one of the harder tasks to not forget. And if you're really doing that, you should have a very good reason to make a data member public in a class, because it's usually about encapsulation. So if you make that accessible by everybody, have a good reason for that. Declare the destructor virtual in a base class if the class should support polymorphic deletion. You will see that done a lot, but it's not always that we give it a deep sort. And declare your member functions that you override from a base class with override. You get more support by the compiler catching errors where you missed the signature. It's a real helpful keyword there. Can strongly encourage you using that. And to quote Scott Myers, never override a non-virtual member function. This also does not give you what you want. It depends on which type of pointer or reference you are accessing this object, which function then gets called. And I would say prefer class when there is a constructor that checks for some invariant and sets some data members because they have a dependency. Otherwise, use a struct. Right? So I hope you learned something. I could share something valuable. We basically are out of time for questions, but we might have time for one or two before we have to close. With that, let me say, I'm Fertig. Thank you. So the microphone is here in the middle. If you have, I think, 2 questions, we might have the time for that. If not, you can also fetch me later. It's fine as well.
Could you expand a bit on the explicit keyword usage?
So can I explain a bit on the explicit keyword usage? Yeah, so there is a rule in place that enables a compiler to use any single argument constructor as a so-called converting constructor. So you can find yourself in a scenario, let's say, one very popular one is you have a function that takes a std string. And what you pass to it is a C string literal. This is where the converting operator kicks in. So std string has a single argument constructor from a char star, basically. We want that, I would say, on average. For other types, if you have your own class type, the function gets called with an integer. Users are surprised that this works. And in the background, you get an implicit object created. So this is why you should think about your single argument constructors. Does it surprise users when this implicit conversion happens? For std string, I would say the answer is no, we want that. So for these type, get rid of the explicit. But for all the others, make it explicit. You can always do that, remove that. That's the easier part. Adding it breaks your code. To 90%, I would say you break somebody in your code base. But removing it, if you learned it's acceptable, so that would be the thing. That would be my expansion to
Thank you.
explicit. You're welcome.
Hello, thank you for the talk. Could you go to the sort example? I think mid-20s.
This one or earlier?
Let's see. The one that showed protected, yeah, this one right here. I've seen another pattern, I think, maybe called NVI. Could you go one step further and change protected to private here?
You can do that.
Because then it also doesn't really make sense for quick sort to be able to call read sort right out of order, right? Just the process method.
Oh no, that's not how it works. So if you make the 3-member functions read, sort, and write instead of protected private, quicksort can still reach them in the normal manner because they are virtual. We are going via the vtable, and that one is not protected as well as others if it comes to derived classes. So,
but a actual object of quicksort, a user can't call them, right? They can just call.
A user can't. So, but in my code already, a user cannot call even in the derived class
right,
because they are protected here. And what you're saying, or what we are saying in combination is, we can make, if it helps, I didn't really want to show that, sort of protected is a little bit nicer, because this is sometimes confusing. You can have, sorry, what I'm doing. It's too early in the morning.
Yeah, so I guess what's the advantage of this then? Because I've seen this pattern a lot.
I would say the only advantage is that it says even more clearly that these things are private. But as I just demonstrate, and this is the purpose, I can still override them in the base in the derived class.
Right.
So it's only visually that you can say, okay, these are private components of my class. It's a little better than protected, but I also saw people in my classes wearing, why can I override that? It's private. It's not supposed to. So I tend to lean more to the protected, but it both works, and I think it's best for you to sort out what's fitting best. If it's not surprising you and your colleagues, if it's private, I would go for that.
Okay, thank you.
You're welcome. All right, thank you very much. Thank you.